I'd like to tell you a story. Imagine flying over a vineyard and not just seeing leaves and rows, but actually seeing the chemistry of the plants. How much water they are transpiring, how much carbon they are fixing, and whether a disease is taking root before anyone can see it. That's hyperspectral technology. My name is Luca Brillante. I lead the Research and Technology Initiative at Fresno State that we'd like to spin out into a company called Hypervid. And in order to transfer the power of this technology from our research labs into the hands of growers and active partners. We like to say, see agriculture like never before, because that's what this technology does. It helps us, it allows us to see inside of plants. So most farming technologies, most farming decisions these days are still taken in the same way they were taken 30 years ago. That means by eye and a few spot measurements. But we can't manage what we can't measure. And so how do we measure? NDVI data, they show you colorful maps, but not necessarily crop physiology. Satellite data are too coarse for plant-level assessment. RGB data are instead too late, because by the time symptoms appear, the problems are already spreading. So every year, billions of dollars are lost into stresses, diseases, and imprecise or incorrect input decisions that could be preventable with better detection. That's what hyperspectral technology does. It allows us to capture light and light interaction with plants across hundreds of narrow wavelengths. Not just 3, like an RGB camera, not just 4, like a multispectral system, but hundreds. That's a continuous assessment of light interaction with plants. And every wavelength is a molecular fingerprint of plant biology. It allows us to see leaf pigments. It allows us to see cell structure, water, and even secondary metabolites. This is molecular level plant insights, and it's operational at scale. So how it works, the sunlight hits the canopy or the plants, and the light interacts with the physiology of the plant. Like some of that light may be used for photosynthesis, and another portion of that light gets back, but it carries the spectral signature of the status of that plant. And that can be actually recorded by sensors that can be driven on planes, drones, or tractors or robotic platforms. This sensor capture image in what we call a spectral cube. That's an image where every single pixel contains a full reflectance spectrum of that light interaction. And then this information can be interpreted through AI models to transform it into actionable insights, which are maps of disease, or stress, nutrient availability, or carbon balance. In other words, we go from photons to physiology, from raw lights to actionable insights. And this is not just a concept. It's actually operational at scale. The last months, we flew over 15,000 acres of vineyards with a system that is able to capture 474 bands from 400 to 2,500 nanometers. That means from the visible to the shortwave infrared. And this system has very high spatial accuracy, about 7 inches pixel, which is 25 times more detailed than the NASA Aviris benchmark system, which is the NASA Hyperspectral Airborne platform. And it's not only 25 times more detailed, but is also double in radiometric precision, with 474 bands against the 280 bands of the NASA system. So what we can do with this data? First, we can assess disease, even before symptoms appear. Second, we can assess water stress, or water content and transpiration in plants. It's also possible to assess nutrient availability. It is possible to assess how much carbon the plants are photosynthesizing, as well as how much carbon is in the top layer or as organic matter of the soil. In other words, transforming sustainability metrics into measurable data. And we can assess how much sugar, acids, and color are into fruit. And of course, all these layers can be fed into robotic platform, enabling them to work autonomously with precision. Here an example. Our virus assessment system detects red blotch and leaf roll into vineyards with 87% accuracy in symptomatic detection, which is 3% higher than what the top level expert can do in the field, and it's 86% in asymptomatic detection, which is even impossible by only visual assessment or RGB cameras, because the symptoms are still not there or visible into the color area. And so we plan to move from vineyards because it's a high-value crop, which demands data-driven management, and it's also an industry which is full of high-tech savvy adopters, and then from there scale up to other trees, row crops, and all the way to the global market, because hyperspectral data is fundamental. So once you prove a concept into one plant, it's easier to transfer that concept into another plant. And so the value of that technology can scale up more rapidly than in other systems. In other words, we not want to only work and build a vineyard tool, but we want to build a system which is the operating system for agriculture intelligence. And so the business models we have in mind is structured and tired. On the left of this diagram, we have an airplane, which is our data service arm. We fly, we capture, and we deliver insights. Then I elaborate it through AI proprietary models in order to transform this data into physiological traits that can be later on served to growers, consultants, and agtech partners through dashboards and API. And final output is growers' ROI, which is less inputs, less disease, higher yield, and overall smarter farming. And then on top of that, we can license data set and AI models so that can be used across analytical platforms, satellite firms, and robotic companies, and allow us to build multi-sector partnerships. And so our competitive edge is into the research work we have done with about 7 years and millions of dollars invested into building a very strong hyperspectral data set, which is backed by strong and hard scientific data, such as molecular data, plant biochemistries, and plant physiology. Our scientific credibility, where our models are based on plant physiology and are rooted on plant biochemistry and evaluated through rigorous peer review. And the ability to already move into this field and build key relationships with tech partners and academic personnel. So that's where it gets exciting. We imagine a world where every field is a living data set that we can measure, monitor, and optimize through hyperspectral vision technology. As sensors flies by or drive, we have the ability to see if the plant needs water, needs fertilizers, or is getting infected. And in other words, this is autonomous farming. It is guided by the lights the plant reflect. If you are a growers, we want to have your data work for you. And then if you are investors, we are building the next frontier for agtech intelligence. Join us in Scale Hyperspectral Intelligence for Agriculture. Thank you.
All right, come on, make some noise for Luca. That was brilliant. All right, next speaker, 10 minutes coming your way. Uddhav Bhattarai, make his way up right now. Welcome, welcome there. Let's hear it for him. Come on, folks, we can cheer him. We can blow the roof off this place. It's not that late yet. We're getting hungry, we're getting hungry. Okay, take it away. 10 minutes starts now.
Thank you. Hey, everyone. I'm Uddhav. I'm postdoctoral researcher at UC Davis. So I work with bioautomation lab. So this is a part of a research project. So precision yield estimation and mapping in manual strawberry harvesting with instrumented picking carts and data pipeline. So this is a part of a bigger project where we have growers actually use soil fumigation to actually kill some of the plant, to some of the diseases and protect the plants from the pathogen. And we have this USDA ARS project. If we combine soil fumigation with broccoli and actually rotate that part with strawberry, then we might be able to actually save money using soil fumigation and rotating strawberry with broccoli. So now you might know every strawberry you eat, that is manually harvested by hand. Robotics is still not there. So since strawberries are harvested manually, we have developed instrumented picking carts that can work with the pickers and actually use that picking carts to develop a software pipeline to estimate yield and generate yield map. So this is the whole part of the project. So during the strawberry harvesting, if you do not know, pickers are actually given with something called a wireframe structure. You can see on the right side that is called carito. And they are given also a cardboard box you might see in the grocery store, and also plastic clamshells that comes around $3 to $5 in grocery stores. So those things are actually used for strawberry harvesting right now. And once a picker completes the harvesting, then at that time, they carry that cardboard box and then move to the outside of the field, that is called headland, where they actually give that tray, get a number of how much strawberry they have harvested, and based on that one, they are get paid. So that is the overall harvesting pipeline of manual strawberry harvesting looks like right now. So what we developed is called instrumented picking cart, ʻāINA. So what ʻāINA has is, we take this commercially scale wireframe structure called carito that is seen on the top left corner, and we add some sensors that can be used by the pickers. So what do we add? We actually add load cells. You can see on the right side, 2 load cells, they can actually measure how much strawberry is harvested. Along with that load cells, we also have GPS unit. You can see that antenna coming outside. That GPS unit also helps to get the location of where the strawberry is harvested. And we also have IMU unit that measures the orientation of picking cart, how it is located inside the field. So we combine all these information to create an instrumented picking cart. And you can see on the bottom right side, so there is a control switch. So we can actually collect the data, run this ʻāINA in 2 modes. One is data collection mode, when you have to go to the field and collect the data, give it to the picker. And another one is the data upload mode, where it can upload the data to the cloud. So this is the picking carts that is used in the strawberry field in Salinas, California. So they start from the center, they go on the other side of the field, and continue harvesting when they complete a row. So we did experiment in 2 fields, Santa Maria, California, and Salinas, California, 4.5 acres of land and 4 acres of land. They are different in terms of the growing structures. The left one uses 4 strawberry plants per bed, so that is big. That is a bit bigger than the right one. So we collected harvest data from April to July, used by the pickers. These are used by the commercial pickers, and around 27 harvest sessions for the Santa Maria and 23 harvest sessions in Salinas. So this is what the data looks like. Now, the data in the sensing system, the GNSS unit we have used is cheap GNSS unit. It does not have RTK. If you include RTK, then it gets really expensive with the centimeter level of accuracy. What we have used is satellite-based, augmentation-based localization system that has around 75 centimeter of accuracy. So we combine these information and give the picking carts to the picker. So these are the raw cart traces, the location of how picker actually pick the strawberry. So you can see a lot of noises. That blue one, that is the storage container. Someone turned on the cart and then just walked around the field. And there is a lot of noise in switching those rows. And because the pickers are given with these carts, they actually tend to rush because they want to make more money. So that is why, due to the manual handling of the cart, there is a lot of noise in the data, and also because of the low-cost sensor that has low accuracy, there is also problem with the data that can actually jump. It shows that a picker is harvesting in one row at a time, and again in the next, after some time, it can show in the another row. So how do we solve that problem? What we did is actually developed a robust data processing pipeline. So in that data processing pipeline, we first really want to know what is the picking area location, where are the pickers are actually picking. And looks like these new deep learning algorithms are actually pretty good in terms of selecting those data when pickers are picking, or not. So, and also you see there is a field boundary. We can also use the field boundary data to remove some of those data. So that is the result that we get after we have actually identified the picking activities and removed some of those noises. You can see those, there are some deep blue colors and also yellow colors. So basically, deep blue color is the starting location of when they started to harvest a tray, and yellow is when they completed a tray and went to outside in the hairland, delivered a tray, came back and started to harvest again. So that is the cleaned up data. But still, there is a problem with the location-related pattern. So in the location-related pattern, what happens is the main problem is the location is not correct. Sometimes the picker is showing picking in one location, but not in. But after some time, it does not show in that same location. So at that time, we use some mathematical formulation on how pickers actually behave during strawberry harvesting. For example, two pickers does not generally stay in a one row if they are harvesting in same direction. You see, they start from the center and go on the opposite side, so they do not harvest on that location. Also, a picker generally does not switch row automatically because another picker is harvesting in another row on the neighborhood. So we use those kinds of information to actually correct those wrong GPS locations to move them back to the correct location. And after that, we get something like this. We can divide the field into the grids and get the strawberry yield map. So that is for one day. But what if we do for season-long yield estimation? So this is what it looks like. So on the left side, that is for Santa Maria, and right side, that is for Salinas field. So on the top left corner, you see all of those reds. So that is the low yield area, and blue is the high yield area. So looks like what happened is later in the season, on the left figure, at that time, there was some soil-borne disease. And because of those diseases, the yield is specifically low in that area. And also on the right side, you can see that square over there. So there were the plant seedlings died around 1.5 months after they planted the strawberry, and then at that time. And the yield started to decrease continuously. So with every harvest session, if we can estimate the yield distribution, we know where the problem is and make necessary intervention based on this information. So that is the overall idea, but we did some analysis, and we found that when the picker is harvesting strawberry manually, around 74% of time they spend picking the strawberries. Now there is remaining 26% of time. What they do is they actually transport those field trays to the headland outside of the field, deliver that, and then receive the empty trays. So they spend that time, around 26% of the time, for that problem. Now we removed the break data when they took a break. We removed any other extended breaks during the data analysis. So there is a really good chance for automation for saving those 26% of time to increase the throughput of strawberry harvesting. And also, you can see average tray fill time is around 6.2 minutes. This is based on Salinas experiment. There are some variation on how this is calculated. For example, the field size, there were only 2 strawberries were planted in a bed, so it might change based on the field, but most of the strawberries are either harvested with 2 plants in a bed or 4 plants in a bed. So basically, they took around 6.2 minutes for harvesting strawberry, and we also estimated how much tray pickers actually harvested. So we got accuracy of around 94%. You can see on the right side, that is the x-axis is for ground truth and y-axis for the estimated tray count, and we got high correlation between how much strawberry is harvested by the picker. So we got this information from grower when they paid the picker. On the x-axis, that is what we got from the grower, and on the y-axis, that is what we got from our algorithm. So we are able to estimate how much strawberry is harvested, trays is harvested with high correlation. So you can see around 14,000 harvested tray, we are able to actually estimate those amount of trays that are harvested by strawberry. So I cannot say this can be used to pay the picker right now. There is still some error with the sensing modules, but this is something that gives the idea of what is the general trend of harvest by the picker. So that is all I have, and thank you so much. I'd like to acknowledge the funding agency that funded the projects and also those who helped running this project. Thank you.
All right, out of UC Davis, go Aggies, Uddhav. All right, next up we have a student-led group represented by Rona Lei Duldulao, and they're from the University of Hawaii. Go Warriors. Give them a warm round of applause, will ya? There you go. Yeah, that was a little warm. I like it. We'll give them a good one. Here they come. And your 10 minutes starts now.
Aloha kakahiaka kako. We are Team ʻāINA from the University of Hawaii at Manoa, and we are here today to present our project, Operation ʻāINAs. This is our team of undergraduate students who helped make this project possible. I'm Rona, and we have Lucas, Zayden, Wilson, Tyler, and Christian speaking today, and we also have Mikkel helping out. These are our advisors who helped us with our project, Jason, Dr. Paul, Dr. Jenkins, and Dr. Chen. They are not attending the conference today, but we want to thank them for their time and work for our project.
Sorry. Okay, so while we're thinking about our project, we, out of the various different farms available with us in Hawaii, and as you guys know, it's a very small place, so we ended up landing on Doe Plantation due to its rich culture and also a unique history within Hawaii. And so one thing that Yaki Rosa, who's a packing manager at Doe Plantation, he gave us various different problems that they're witnessing inside of their fields today, and those being labor shortages, aging farmer population. And those two issues cause more problems for the company, those being food resiliency, which not only they rely on for profit, but also the community as a whole, being able to distribute and disperse foods, not even just to Hawaii, but internationally as well. And also, all of these issues can't be solved due to the expensive automation, and all the equipment needed is starting to increase. And yeah. Okay, so I'm going to give you guys a little bit of statistics. So the average age for farmers are approaching 60, and Doe Plantation actually ranges between 50 to 70 years old. And also the labor costs, it may be a good thing that the wage for these farmers are increasing, but it's also a negative, because as the wages increase, they can't hire as many workers. And also the operation costs are also increasing as well. As I mentioned, the prices for implementing modern technology is causing this issue for them. And yeah, so we broke our project up into 3 different phases. This past semester, so about like 10 months of work, we finished phase 1, which was the vision-based section, training a farm intelligent AI program. And then we're gonna talk a little bit more about phase 2 and 3, which we started phase 2 this past month, and phase 3, which is our future plans. Phase 2 being the implementation of hardware and teleops, and phase 3, the VLA training, and ultimately the deployment internationally. Yeah.
So, for phase 1, we worked with Doe Plantation on Oahu, and we developed a drone and land robot system for their farm. So our drone system works on identifying pineapple blooms for field-level pineapple counting, and our land robot collects images in the field of pineapples for 3D volume reconstruction. So these systems help with the farm's labor shortages and their operational costs.
So the first component of our solution is fruit level perception, where we leverage computer vision for pineapple size estimation. The first step is 3D reconstruction using Pi3, a state-of-the-art deep learning network, which uses permutation equivariance to allow for robust and quick 3D reconstructions compared to traditional structure from motion techniques. Next is mesh processing, where we use Facebook's segment anything model to select the pineapples from the environment of the 3D models using a pineapple similarity loss function. Lastly, we then compute the convex hull from the isolated pineapple 3D models. With the volume, farmers are able to get actionable insights into the maturity of their crops.
All right, so next up is the air-based component, where we go over the counting of the actual pineapples. Oh, I have it. This one? Okay. So the first step, we have to do some data processing, of course. So essentially, we have our drone, and it surveys the entire field, and we need to ensure that our machine learning models have good, clean data that does not have repeated segments, basically. And so this is just a problem with our data set, essentially. You could easily do this with an algorithm that's running on the drone, but it's fine. So first off, the drone surveys the field. It captures all the images. There's going to be a lot of overlapping data, as you can see in the image there, and overlapping causes the double counting issue. So what we can do to fix this is by creating a panorama that essentially only has the singular individual data points. So we can do this by looking for prominent features in the field and then matching them with other features in other images in the adjacent images in the data set. And essentially we can run a complicated algorithm that will merge this data together, and I will explain that more. Yeah, if you come talk to me later, because it's a lot to talk about, so I won't go into it here. But essentially, it's a cool algorithm that finds these feature descriptors and links them together and stitches the images all together. And so the result of this is that we get many images. I said 100 plus. It's probably more like 1,000 plus images, and we can essentially generate a large panorama of the entire field. And with that, we can do this.
Yeah, so once we have our stitched image, we basically have the entire field in one image, so we can finally run our object detection model on this field. Our object detection model is trained on our pineapple data set, which detects things such as pineapple crowns and weeds. But we're going to focus on the crowns here. Our model will begin by drawing bounding boxes around pineapples that are ripe and ready for harvesting. And this will provide farmers with a count in the entire field of how many pineapples are ripe. And if you go to the next slide, this provides a lot of useful data visualizations. For example, in this chart, farmers are able to see and are able to have an oversight throughout the year and the season of when peak harvesting season is. And in this way, they can optimize labor timing, and they can send out their workers during peak harvest seasons and during off-peak hours. And when not many pineapples are ripe, they can use their workers for other farming tasks.
So this past semester with our project, we were able to win the productivity award under the Farm Robotics Challenge. So yeah.
And as we finished with our project for the Productivity Award, we're going to be moving into our phase 2, as we mentioned before. We'll begin to prototype our teleop stations, as well as automating our robot arm. So as you look on the slides here, we have been simulating our robot arm. So we have a picture of our robot arm picking up on avocado and orange. Currently it's remote controlled, which will soon to be automated. And with that, as we go into phase 3, we will begin to put this teleop and the automation together to create a fully automated operation. So that means we're going to be able to have the robots move on their own, pick up fruits on their own, just fully automate everything. Thank you.
Oh, let's hear it for him. Okay, that was awesome, guys. Way to go. I thought we were going to hear one more. That's amazing. We're going to keep these lightning talks going lightning fast. Hey, next up, out of the University of Minnesota, go Gophers, Graham Wilson. Yeah, you know what I'm talking about. Make some noise. All right. We got Graham and then one more, and then we're going to get you to lunch. It's exciting. And your 10 minutes starts now.
Okay. Hi, everyone. Thank you so much for coming here to listen to me talk today. My name is Graham Wilson. I'm a mechanical engineering and computer science student at the University of Minnesota. I work in a robotics research lab, and I was also the hardware lead for this project, which started out as a submission for the Farm Robotics Challenge, which is the same thing these guys did. The whole idea is to find a farmer that has an issue and then try and solve it with robotics. So the main problem that we came up against, that many of the farmers we spoke with told us about, was that deer are eating their crops before they can harvest them. In the Midwest alone, deer eat $8 to $10 million worth of crops every year. And the farmer we spoke with estimated that 30% of his crops every year were eaten by deer, and all of the beans were eaten. So a lot of the other deterrents that exist out there work in some sense, but they also have some major drawbacks. One main thing that, of course, does solve the issue is building a tall fence. One downside is, of course, you have to build it quite tall so that the deer don't jump over it. It restricts tractor movement because you can't turn around to till and do other tractor operations. And then, of course, it costs a lot of money to install the fence. You have to maintain the fence, and so forth. So other attempts at keeping deer away from crops include motion-activated repellent devices. This is like sirens or propane cannons. These do work at first, but I think deer are pretty quick to realize that the propane cannon isn't going to scare them away from the farm. Other options are like odor and taste-based solutions that can be sprayed on the crops. Of course, this comes with a cost, and you have to keep reapplying them, and then there's also an environmental aspect of spraying the chemicals. And then finally, you can try planting deer-resistant crops, either as a barrier or interspersed. But of course, this adds complication to farming operations. So what we aim to do is integrate modern drone-based technology to combat this. FarmGuard is a comprehensive drone-based solution that will jointly use stationary cameras and periodic energy-efficient flight patrols. So it's built in with obstacle avoidance. So what the drone does is it flies around the field using energy-efficient path planning and searches for deer. So we designed a model that detects deer. So it flies around. Once it does detect the deer, it changes to herding mode, where it will fly around the farm and then chase it off the property. So some of the features of FarmGuard are the state-of-the-art path planning and computer vision algorithms that we created for it, the integrated GPS module that uses an RTK base station to have high accuracy for flying around and then also for landing, and then lights and speakers for deterrence. There are lights and speakers on it, but it's also been shown that just the presence of the drone flying around is pretty effective at scaring away deer. So this project was completed with a team of 25 University of Minnesota graduate and undergraduate students. There were 3 teams: the hardware team, which we worked on constructing the drone and then prototyping the charging station. The drone behavior team, which worked on the algorithms, and then the computer vision team, which worked on the computer vision and then also testing it in a simulated environment. For our efforts, we were awarded the Excellence in Small Farms Technology Award, which we were pretty excited about. Thank you. So we're really excited about this project. It was just the beginning. We only had 3 months to work on it. First of all, we're working on prototyping and building a charging pad as the hardware team. Our drone behavior team is working on the herding algorithm to get the deer off. And then also we're developing an app which could be used to set boundaries, set patrols, and choose herding behavior, such as maybe wanting the deer to go in one direction versus another if there's a road or something else. And that's our project. We're really excited to keep working on it, and thank you all so much for for coming to listen.
Come on, let's hear it for Graham. That's awesome. Congrats. All right, our final speaker. Let's make some noise all the way from the University of Georgia. Go Bulldogs. Luan Pereira de Oliveira. Yeah. And your 10 minutes starts now.
Thank you. Good morning, guys. My name is Luan Oliveira. I'm an assistant professor and precision ag extension specialist at the University of Georgia in Tifton. My crew is right here. Can you lift? Can you stand up? Rajamar, Victor, Marcella is right there. We won the Grand Award with the Farm Robotics Challenge this year. And we built spray drone dock, okay? I'm gonna talk a little bit about that in a second. I could start this presentation with a problem, but that graph is actually a solution. You know, a lot of technology coming up to the market these days, right? That specific graph is a DJI agricultural drone sales by 2021. And those are not only spray drones, those are ag drones, okay? They had sold about 135,000 drones through 2021. But then when I saw that number from last year, 400,000 drones, it scares us a little bit where the technology is going, how we're going to use it. And DJI is not the only drone manufacturer on the market, okay? So that's why we came up with a solution for a problem that is invisible. We have, you know, high tech, but not always. The drones are there, but the growers, they're mixing the chemicals. They're actually doing the same as they did back in the days. They're mixing the chemicals like that. They're dosing the chemicals like that. And they're also still doing the same manual calculations. Who knows when you get a label from a product here, when you're going to apply on the farm, there's a label. It's like a medicine. It tells you how many ounces of that product you have to apply. If you can apply with more than X wind speed or Z wind speed, what is the droplet size of that specific chemical that you have to comply with that because those are federal regulations. So the grower still calculates doses and mixes everything by hand. What are the problems with that? Okay, the first one is that the manual calculation is time consuming. As a calculator, say, hey, I have 10 acres, actually I'm put like 17 acres, and I have to apply 1.33 ounces per acre. So he has to go there, input those numbers in his calculator and say, okay, I need X ounces. Second one is that inconsistencies in volume can lead to over or under applications of those chemicals. That's another one, and that can lead to a major problem, which is called resistant. Bringing back to the human life, if we take a smaller dose of a medicine and we have like an antibiotics, that bacteria or that disease is not going to go away, is actually going to create a resistance to that medicine. That's the same with ag chemicals. If you underdose a herbicide, that herbicide is not going to work really well with that plant. That plant can create resistance for that product over time. And we have seen that happening a lot these days. Those are good, I would say, examples I just gave. This one is the worst one. We don't, sometimes people don't use and dose those products. They actually just throw from the container, or they use the cap to dose the chemicals and put inside of the tank. Growers cannot afford wasting farm inputs. And this graph here is really shocking because it shows the inflation of farm production expenses from 2020 to 2023. And pesticides, they are third place there, with 66% of the prices increased. That's why I want to talk about balance with you guys. I like to bring my horse meme graph, that's what I call it. Imagine a really nice, beautiful horse. And this is a chemical, it represents a chemical application. You have a high quality input, a high quality equipment, a high quality product dosing, high quality mixing, and a high quality application as well. You did your homework, okay? But then imagine that you start with high quality inputs, you start with high quality equipment, you do more or less on dosing, and then you do poor quality tank mixing, and then you don't spray well. That's basically what happened in every single ag operation, okay? That's why we built what we call Spray Drone Dock, a launch pad to the future. As the FarmNG lady said, and I stole her phrase, her slogan, this is a fully automated spray drone supporting operation system, okay? It has an app, a built-in app, that helps the grower to calculate how much of this chemical he needs, how many tanks per acre he's gonna need as well, how much water, everything. And in the meantime, it doses those chemicals for the growers, and it mixes those chemicals with clean water. And after dosing and mixing, it also delivers the chemical to the drone. And the drone takes off from the platform, goes, sprays the crop, and comes back. So if you've ever done a spray drone operation, you know how heavy those things are, right, Justin? They are really, really heavy. And again, everything is a set of, I would say, pumps, hoses, solenoids, and intelligence behind the whole system, and an app. Okay, we did trials, of course. So our preliminary trials, actually a lot of trials, this data is not preliminary anymore, showed us that our system is 99% accurate. So pretty much that a human being does by hand, the system is gonna do with high accuracy. And we were also 10 times faster than a human being doing the calculation, the dosing, and the mixing by hand. You could ask me, but Luan, there are systems on the market today, right? And there are what we call huge drone, what do you call it? Spray drone trailers. Those trailers, most of them, they don't have intelligence, the app that I just showed you guys, and they're just basically a set of tank, hoses, generator, and then pumps and the nozzle to deliver to the drone as well. And then ours, we have the land pad, we have a battery charging station, the generators are there, a 39-gallon tank, and I'm gonna talk about this in a few minutes, actually in a minute. The brain, automatic chemical calculation, dosing and mixing, and the delivering system for the drone as well, and everything is mounted on a robotic platform. Who we want to target with our system? Right here, this graph from USDA shows that 86% of the US farms today is made of small family farms. And then from the whole acreage of the United States, 41% is also from small farms. So we don't want to go to the big guys. That's why I just mentioned about a small tank. We want to help small farmers, small growers, to tackle that issue, which is actually not an issue, of technology in their fields. With that, I'll be open to questions if you guys have any. And there should be an end slide right there. Thank you.
All right.
How many different chemicals can you mix? 3 at a time. Yes, we can. And actually, that's something we always put like chemical 1, but you can actually say, hey, do chemical 2 first, and then mix and matching.
Do you ever see yourself getting into a point of having almost like a library of
That's the point, because in my slides, I showed different containers for dosing the chemicals. Those containers, they're based on the density of those products. So each product has its own density. So we want to have a library. And then the model is going to actually calibrate itself, like the pumping, according to that specific density. It's a lot, I know.
Do you also see yourself having more intelligence as to the rates and like the potency? I don't know the right word, but like when you're mixing for aerial application, it's a little different than most people have experience with.
Yes, yes. Actually, it's currently adaptable. So we can do like half an ounce. It's pretty low, like the accuracy that we can do. So that's why it can be scaled up, but right now it's meant for those like really smaller doses. Okay, thank you, appreciate it,
All
guys.
right, let's hear it for him. Hey, let's hear it for all of our presenters. Big round of applause.